Hey everybody, welcome to AlgoExpert. In this video, we're going to be covering the question of the power set. This is a pretty famous question. Basically, it asks you to write a function that takes in some set of elements. For the sake of argument, let's say that it's an array of numbers, of integers, and it wants you to have that function generate the power set of that array of numbers. The power set is something in math, and it's defined as the set of all subsets of another set. So in this example, we've got the array 1, 2, 3, the numbers 1, 2, 3, and the power set of this array, or of this set of numbers, is going to be this here. We have the set in question, 1, 2, 3. Then we've got all subsets of length 2 of 1, 2, 3, which are 1, 2, 1, 3, and 2, 3. Then we've got all subsets of length 1, which are 1, 2, and 3. And then finally, we have the empty set. And so that's the question, okay? The question, just to make sure that we're on the same page, it asks you to find all the subsets of the set, and a subset doesn't care about order. In other words, 1, 2 would be the same as 2, 1. So we don't have 1, 2, and 2, 1 in the answer. We just have one of the two. All right, so how do we solve this problem? There are two ways to solve it. One is iterative and the other is recursive. Or in other words, there are two algorithms that we can kind of use, and one is iterative, the other one is recursive. I do believe that the iterative solution is a lot simpler than the recursive solution, and I think that you'll agree with me, mainly just because it's more intuitive, and it's fewer lines of code, and it makes a lot of sense once you kind of wrap your head around it. The recursive solution is a bit tougher. But so what we're going to do here is we're going to cover the iterative solution in this conceptual overview. Then we're going to go over it in the code walkthrough and write it out. And then in the code walkthrough, I'll also write out the recursive solution and explain it as I go. But I don't think that covering the recursive solution on the whiteboard here will be too useful because it just makes more sense as you're coding it. Anyway, so let's dive into the iterative solution. Basically, what you're going to want to do is you have your input array, right? The set for which you're trying to find the power set. And in our example, that set is 1, 2, 3. And then you've got your final array of subsets, which we can put maybe at the bottom here. And so your final array of subsets starts out empty, right? You don't have any subsets yet. But does it have to start out empty? Can you actually put a value in there right off the bat? And the answer is yes, you can. You can actually immediately put the empty set because you know that the empty set for any set that you're given, the power set at the end is going to have the empty set. That's just part of the definition. So you can initialize this subsets array at the end to hold the empty set. And then what you can say or do is you can loop through your array here, your array of numbers, and start generating new sets based on whatever the subsets you have here, and add them to the subsets array. So, like I said, iterate through the numbers, and at each number, iterate through all the subsets and create a new subset with that number. So let's actually go through an example. We start out at the number 1. So we go through all the subsets that we currently have in our subset array, and we generate a new subset with the number 1 based on the subsets that we have. So we have here only the empty subset. So we can create a new subset with 1. Okay? Now we move on to 2. Okay. Just to clarify here, why did we create a new subset with 1? Well, we took this empty subset and we added 1 to it, and took that newly generated subset and added it here. So now we have 2. So let's move this green line here to show that we are at the number 2. So now we go through all of the subsets that we have, and we add the number 2. So we're going to add 2, and we're going to add 1, 2. Okay? Because we took the empty subset and we added 2 to it. That gives us 2. And then we took the subset with 1 in it and we added 2, and that gave us 1, 2. And lastly, we get to this 3. So now we can put our green underlining thing here under the 3. And we iterate through all the subsets that we have. So we start with the empty set, add 3 to it. So that gives us, whoops, not in purple, that gives us 3. Then we have the subset 1, add 3 to it. That gives us 1, 3. Then we have the subset 2, add 3 to it. That gives us 2, 3. And then we have the subset 1, 2, and add 3 to it. That gives us 1, 2, 3. And you'll notice that we stop here because every subset afterwards was added with the number 3. In other words, when we started, when we got to this number 3 and we started generating new subsets, we only had these 4 first subsets here before this white line. And so then we generated these 4 new subsets, and we don't add 3 to them. We just generate them and then don't touch them. But so that's it. This is our solution. This is the same array that we have up here, just in a kind of different order. But that's the solution. So let's talk about the space and time complexities of this algorithm. The way we can come up with the space-time complexities here is a bit different than a lot of other algorithms. Usually in other algorithms, you think, okay, how many for loops do I do? How many, what computations do I do? Here you'll notice that it's kind of tricky to come up with that because you're generating new subsets every time. Every time you loop through the numbers here in your array, you're generating new subsets. So you keep making any for loop that you might have in your algorithm take longer and longer. But so it begs the question, what is the time complexity? How do I come up with it? And so one way of thinking about it is, well, how many subsets do I have at the very end, right? How many subsets am I going to have? Because if we know how many subsets we have, then we can figure out how we generated them or how long it took to generate them, right? And so to figure out how many subsets we have, either you could know the math formula, like there's a proof behind the number of sets in a power set, and it turns out the answer is 2 to the power of n. There are 2 to the power of n subsets. But how do you know this? Well, what you can do is you can notice that at the beginning, we start with one array. We start with one subset. Then we doubled it. We had one subset and a subset with the number 1. So we go from one subset to suddenly 2 subsets. Then we doubled that. We went to 4 subsets. And then we went to 8 subsets, right? These lines that I'm doing here kind of show how we increased our subsets. So every time we're doubling the amount of subsets that we have. Every number that we loop through, we double the amount of subsets. So what does that tell us? we double every time and we have n times, so we have 2 to the power of n subsets. So once we know that we have 2 to the power of n subsets, we can say, well, how long does it take us to create these arrays, right? Every time we have to append an element. That's an operation, right? And these subsets are at most of length n, right? Like this one has length n, 1, 2, 3. At the least, they have length 0, like the empty array. And on average, here we've got length 1, we've got length 2, all the way up to n. So we've got an average length of roughly n divided by 2, right? Half of n. So that means that it took us, time is going to be equal to O of 2 to the power of n times n divided by 2, which converges to 2 to the power of n times n. And that's going to be the time complexity of this algorithm. And then in terms of space, it's going to be the exact same thing. So space is going to be equal to O of 2 to the power of n times n, because, again, we're storing 2 to the power of n subsets. We've got 2 to the power of n subsets in total. And then each of these subsets has, on average, n divided by 2 elements. So multiply that by 2 to the power of n. Get rid of the divided by 2, because, n divided by 2 converges to n in terms of complexity analysis. And so we've got a space complexity of 2 to the power of n times n. And that's the solution. This is how you solve this problem iteratively. As I said, I think that this becomes pretty intuitive, especially when you see it written in code. It's relatively easy to wrap your head around. I mean, it's not the easiest algorithm to come up with. It's definitely a relatively difficult question, but the iterative solution makes sense. So we're going to dive into it now, and then I'll give a brief overview of the recursive solution, which is a bit tougher. All right, so we've got our power set function defined. It takes in an array. And the first thing we're going to want to do, for the iterative solution at least, is to declare our subsets array. And so as we mentioned in the conceptual overview, we can initialize this subsets array to hold just the empty set, or the empty array, because we know that's going to be in the power set of any array that we might be given. And so then we can start iterating through all the elements in our array. Now remember, we're not necessarily only dealing with numbers, we're dealing with kind of arbitrary elements. So we can say for LA, short for element, in array. And then here we iterate through all the current subsets that we have in our subset array. So here it's important to note, and I mentioned this in the conceptual overview, we're only generating new subsets based on the subsets that we currently have at the beginning. Like when we reach a number or an element in our array, whatever subsets we currently have in our subsets array, those are the subsets that we want to use to generate new subsets. But we're going to be adding these new subsets that we generate to the subsets array, and we want to make sure not to keep looping through those. So here we want to say something like for I in range len of subsets. So here, this len of subsets value is going to be calculated kind of at the beginning of the for loop, and then it's never going to change. So we're not going to get into some kind of infinite loop. So for I in range len of subsets, current subset is going to be equal to subsets of I. And then we can say subsets.append current subset plus LA. We can generate a new subset that is composed of the current subset and an array containing just the element that we're at. And that's it. That's it. Once we get out of these for loops, we can just return the subsets. And so this algorithm is going to run in O of n times 2 to the power of n time, right? And it's going to run in n times 2 to the power of n space. Why does it run in that time and space? Well, remember, we've got 2 to the power of n total subsets. You can get to this either mathematically, you can prove this by induction, though you probably don't want to do this in an interview, or you can just notice that whenever we, in these for loops, at every element in the array, we're basically doubling the number of subsets. And so that tells us that we've got 2 to the power of n subsets. And then naturally, if we've got 2 to the power of n subsets, it's going to take, and each of these subsets have on average n divided by 2 elements. It's going to naturally take roughly O of n time to generate each of them or to store each of them. And so we multiply n by 2 to the power of n for the total number of subsets. And that's it. This is the iterative solution. It's a pretty cute solution code-wise. In other words, there are very few lines. It's pretty straightforward, easy to understand. Now we're going to cover a recursive solution, which, as I mentioned before, in my opinion, is a bit tougher, but it's still pretty cool to understand and explore nonetheless. And perhaps you'll find it simpler. Some people think better through recursion. Some people think better through iteration. The way we can think about this recursive solution is that for our iterative solution, you saw in the conceptual overview, we had the array 1, 2, 3. We generated all the subsets that had the number 1 in them. Then we generated all the subsets adding the number 2. Then we generated all the subsets adding the number 3, and so on and so forth. And so you can kind of imagine with recursion that if we call the parset function on the first array 1, 2, 3, we might want to first generate all the subsets, or we might want to generate the parset of the array 1, 2, and then add to that parset all the subsets that would have the number 3. You see, so in other words, we can kind of if we have a subset that's 1, 2, 3, 4, ... x, the parset of this set is essentially p. The parset of this set is essentially equal to the parset of 1, 2, 3, 4, ... x minus 1. And then plus you add to all the sets in this parset, you add the element x. This is just like pseudocode here, but to all the elements in this parset, you add the element x. And so on and so forth. And that's how you can kind of go at this recursively. So what we can do here with this parset function is we can pass in another index, or another argument, which we can call index and initialize to none. So the first time someone calls this parset function, it's just initialized to none. And we can say if idx is none, then we can say idx is going to be equal to the length of the array minus 1. Okay. Otherwise, if idx is if the idx is less than 0, we're going to return the empty array. That's going to be kind of our base case. And then the current element that we're at is going to be Ella equals to array of idx. So what are we doing here? Okay, let's explain. We're saying that when someone calls the parset function on an array, at the beginning they're not gonna pass in an argument, so we initialize idx to none. And if idx is none, then we set idx to len of array minus 1, the last element in our array. We set this index variable, whatever it's gonna whatever purpose it's going to serve, to point to the final element in the array. If we ever get to the point where our index is less than 0, then we return an array containing the empty array. That tells you that's going to be our base case. Otherwise, if we don't hit either of these cases here, we're going to go down here to initialize our element to be the thing contained at the index in our array. And so then we can say the subsets here are going to be equal to the power set of array index minus 1. In other words, like, let's say our example here, our example set is 1, 2, 3, 4. We're saying here that LA is going to be equal to 4, and our subsets are going to be equal to power set, I made a mistake here, power set of array IDX minus 1, which is going to be 2, right? Because if we've got 1, 2, 3, 4, then IDX is going to be 3, right? The index at which 4 is stored is 3. So IDX minus 1 is going to be 2. In other words, this is going to be the power set of 1, 2, 3. Okay? So we're saying when we've got the array 1, 2, 3, 4, the current element that we're looking at is 4. Then we generate all the subsets of 1, 2, 3, the previous 3 numbers. And then we can say for I in range len of subsets. And here we can have the same exact logic as we had above here. So for I in range of len of subsets, current subset is going to be equal to subsets of I. And then subsets, we're going to append to them current subset plus LA. And then we return the subsets. So the idea is, like, we call this function on 1, 2, 3, 4, right? Here, let me write it down here. We call this function on 1, 2, 3, 4. And here we say LA is going to be equal to 4. And then subsets is going to be equal to power set of 1, 2, 3. And so now, here, we call the power set function on 1, 2, 3. And so here, LA is going to be equal to 3. And subsets is going to be equal to power set of 1, 2. And so on and so forth, right? We keep going down like this. And then once we have a power set here, we can say add 3 to all subsets in the power set of 1, 2, 3, right? That's what we're doing in this for loop. And that's the same thing that we were doing in the for loop of our iterative solution. And then the entire reason that we're using this index business here is just so that we don't have to, we can use pointers instead of like sending copies of subarrays here. Like here, we could do something like, here, let me delete all of this to make this a bit less confusing. But like here, we could have done subsets is going to be equal to power set of array, and here we could slice, right, from 0 to index minus 1 or something like that. But if we do this, then we're doing an additional, like, then operation, right, of slicing. Because slicing an array is essentially copying an array, and that's an then operation. So instead of doing that, we can just use this pointer logic with this index, which kind of tells us, what element we're at. So here, if we get to index 1, our element is going to be the value stored in the array at index 1, and then we're going to call the subsets or the power set function with index 1 minus 1, which is going to be 0, and so on and so forth. But so this is the recursive solution. I hope that this explanation was relatively clear. Like I said, in my opinion, this is a bit more complicated to wrap your head around. Though once you do wrap your head around it, it makes a lot of sense, right? Like the power set of 1, 2, 3, 4 is the power set of 1, 2, 3 with 4 added to all those subsets. And then the power set of 1, 2, 3 is the power set of 1, 2 with the subset with 3 added to all those subsets, and so on and so forth. But it is pretty difficult to come up with at the beginning. It's going to run in the same space and time complexity because at the end of the day, you've got the same amount of subsets, and so the same sort of logic can be applied. And the recursive calls, which are going to be stored on the call stack, are not really going to affect the greater space complexity of O of n times 2 to the power of n, so that doesn't really change. And that's that. This is the algorithm. I hope that this video was helpful. I hope that it kind of shed some light on both of these solutions, iterative and recursive. And I'll see you in the next video.